All right, guys, we're going to finish up chapter 13 today. Welcome to section D. We're going to keep talking about our simple machines. And our next one is known as an inclined plane, okay? Also known as a ramp, okay? So this would be considered an inclined plane. So imagine I had to lift an object this distance right here. Rather than lifting it up straight off the ground, full force against gravity, it would be easier to push or pull it up this slope. That actually reduces the amount of force needed to get it up the same distance, okay? The input force is what you put into it. Okay, let me get my pen here. So this would be the input force. I'm pushing, this is just an example of a piano. This is actually on page 314 of your book. We're going to talk about the calculations on 314, okay, if you want to follow along. So the input force is what you put into the object to get it to push up the ramp, okay? The output force is the weight of the object itself, okay? So here's the output force. If I were to pick that piano straight up, it would have a weight of, or force of 3,125 newtons, okay? So you can already see the reduction in the weight by just pushing it up a ramp, okay? The input distance is how far you have to push it. So it's the length of the ramp, okay? And the output, I have force here. This should say distance. The output distance is the distance above the ground. So there's the output distance. That doesn't change, okay? So however high you're trying to get the object, that is its distance. That's the output distance. The input distance can change, though. I can change the slopes of my ramps. So I've got two ramps here, okay? They both go up to the same point. One is clearly steeper than the other. So the striped one is steeper than this plain one here. The longer my input distance, the better my mechanical advantage is going to be, the easier it's going to make it, okay? Because what I'm doing is I'm multiplying, actually for the ideal mechanical advantage, where'd my little pen go? My ideal mechanical advantage is I'm dividing my input distance by my output distance. Okay, so if I've got two ramps that have the same output distance, the longer input distance is going to give me a much higher ideal mechanical advantage, meaning it makes it easier. And that should make sense. Pushing something up a steep slope is going to be more difficult than pushing it up a less steep slope, okay? So the longer the ramp, the higher the mechanical advantage, okay? We've got some other different inclined planes here. We have something called a wedge, which is basically two inclined planes put together, and they make this kind of pointy object, okay? What a wedge does is the sharp part goes into whatever object it is. And as it pushes down, it spreads those objects apart, okay? So my input force is the push. My output force is being exerted towards that object, okay? And common examples of that are an axe, a knife. If you've ever seen anybody splitting wood, that wedge enters the wood, and as you put the force on that wedge, it makes the log split into smaller pieces. Your teeth, your incisors are also wedges. If you feel them, they're narrower on the bottom, they're pointy on the bottom and much wider on the top. So every time you bite into food, you're using a wedge, okay? That's how it separates the bites, okay? Now, if I take an inclined plane, so here is an inclined plane, and I wrap it around a cylinder, I will get a screw, okay? And you can see, let me try to do this straight. I went out crooked. That's pretty good. There, you can see that little spiral shape happening there. So basically the threads on a screw are nothing more than an inclined plane wrapped around a cylinder, okay? So screws themselves are an example, but also anytime you have a screw cap, if you think about putting a lid directly onto a container, it takes more force to get on there versus just twisting it into place, okay? The steepness of the threads also has an effect on how easy or hard it is to get a screw into a piece of wood, okay? But that's another simple machine there. So we've got our 6 simple machines. We can actually combine them, and most of the time we actually do combine them. Even the scissors I showed you, that's a combination of 2 levers, okay? So these compound machines are a combination of 2 or more simple machines, and they continue to make the work easier. The mechanical advantage is equal to the product of the mechanical advantage of the separate simple machines. So if I have a lever with mechanical advantage of 2, and I have a wheel and axle with a mechanical advantage of 3, I would have an overall mechanical advantage of 6. You're not going to have to calculate that. But you can see how very quickly, when these machines are working together, these simple machines are working together, things get easier and easier. So I have a couple of examples here. Your parents might have one of these. This is kind of an old school bottle opener, wine bottle opener. And it uses a screw with 2 levers, okay? So you raise these levers up, and what that does with these gears right here is it pushes the screw into the cork, okay? So then to get the cork out, you squeeze these levers back into place, and the gears pull the cork out, okay? A compound machine. Bicycle combines levers. The handlebars are a lever to turn the wheel and axle, obviously, on the wheels themselves. The chain acts as a pulley. There's gears, there's screws holding things in place, so all kinds of simple machines there. The fishing pole, the hook on the end of the fishing pole is a wedge. The reel is a crank, so that's a wheel and axle. There's strings wrapped around it, so it's considered a pulley inside. The end of the rod itself, because the reel, if you're reeling something in or trying to pull a fish in, that's going to be your pivot point. So the extension of the rod is considered a lever, okay? All kinds of crazy stuff. All right, that's it. End of the chapter. Bye-bye.